Okay. Um, now, look at the schedule that we have for assignments. First one being due today, but as I've mentioned at the beginning, that's something I'm pretty loose about. Um, but just if you end up turning in something late, just try not to fall too far behind because assignments will keep coming. Um, okay, and also keep in mind there are a grand total of um, 9 homework assignments. Yeah, 9, but the lowest 2 are dropped. Okay. Mm. And whenever we have a test, of course, there's going to be a gap in homework due dates, so that might be a chance to catch up if you fall behind. All right. So we have a very narrow topic uh, to focus on today. Um, so dealing with lesson 6 and homogenizing boundary conditions. Um, so last time I introduced separation of variables. That's useful for solving certain linear PDEs that have certain properties. For instance, they must have the PDE themselves must be homogeneous. The boundary conditions must also be homogeneous, meaning that um, whatever boundary value you're setting, whether it's the value of a solution at the boundary or the value of a first derivative at the boundary or some combination thereof, so a Dirichlet, Neumann, or mixed boundary condition, that value must be set, that expression must be set equal to 0. So that's what is meant by a homogeneous uh, boundary condition. So, and that's what you saw in the example last time. Um, so here we're going to talk about the case. What happens if the boundary conditions are not homogeneous, something is set equal to a not-zero value? It turns out that we can simply change the problem. We can transform a problem into one where the boundary conditions are homogeneous, and then you can make use of separation of variables technique from last time. So I'm going to go through some examples and then at the end state a general procedure or how we transform a problem to make the boundary conditions homogeneous if they're not. Um, hopefully everything works okay with the video. It's good, of course, a little different today since I'm working from home. Uh, I expect that this will be only for today. Everything should be back to normal for Wednesday's class, and I'll be back in Summit Hall. Okay, so here's a sample initial boundary value problem that we'll consider. So we have the same PDE that we've been dealing with, the heat equation, on some domain, x going from 0 to L. And then we have u, the value of u at the boundary points, set equal to some given values k1 and k2. So at x equals 0, the solution is k1. At x equals L, the solution is k2. So in this case, for a heat equation, the temperature is set equal to these values at the endpoints of the rod on which you're modeling temperature. And then we have some initial condition. So the way we're going to transform this problem into a similar one that has homogeneous boundary conditions, in other words, making these values 0, is to decompose our solution little u of xt. So here's a solution of our original problem. We'll break this down into capital U of xt. This is what we're going to solve for in our transformed problem. And then we have this other function, capital B of x here. So the idea here is this solution satisfies the original boundary conditions. This function also satisfies the original boundary conditions. Therefore, capital U of xt will satisfy homogeneous boundary conditions. So the same types of conditions except these values will be 0. So we're handling the boundary conditions here, everything else here. Now, notice that the solution of our original problem and our new problem both depend on our functions of x and t. Here we have a function of only x. And in this case, we can do that because the boundary values are constants. They do not depend on time t. Now, in our next example, we will allow these values to depend on t, in which case we have a function of x and t here. But we'll deal with a simpler case for now. All right. Now, we're also going to have, now this original solution is going to satisfy this PDE. And what will happen is this function, capital U, will also satisfy the same PDE. By linearity, if this is a linear PDE, this function must satisfy the PDE also. Now, b is a function of only x, not t. So the derivative of b with respect to t must be 0. There's no t dependence. That means that if we plug capital B into this side of a PDE, we must also get 0. In other words, the second derivative must be 0. And for that to happen, b needs to be a linear function of x. Because anytime you have a linear function of x, its second derivative with respect to x has to be 0. So we want to find a linear function that satisfies these conditions. At x equals 0, it's equal to k1. X equals L, it's equal to k2. Now, this is a problem that you actually know how to solve from lower level math courses. You're trying to find the equation of a line that passes through these 2 points. But what I like to be able to do whenever possible is give more of a formula for the solution. And that's what I'm going to do here. Because if you have something like that, then it can cut down on mistakes. So, and this is something that can be useful in a number of contexts anyway, and will help with more general cases that we'll see later. I'm going to show you what is called Lagrange Interpolation. Now, this is actually a concept that I teach about in one of my other classes, Math 460, Numerical Analysis. But here we're using it in a context that you're familiar with. Again, finding an equation of a line that passes through 2 points. So the idea here is I want my linear function to equal k1 when x equals 0 and k2 when x equals L. So what I do is I multiply these values I have, k1 and k2, by linear functions that have certain properties. Now, what are those properties? I want this fraction here to be equal to 1 when x equals 0 and equal to 0 when x equals L. And you can check that yourself here. If I plug in x equals 0, top and bottom will cancel and I get 1. If x equals to L, the numerator disappears, so the whole thing is 0. And then the opposite situation over here. I want to multiply k2 by a function that's equal to 0 when x equals 0. And you can see what happens if I plug in x equals 0 here. And equal to 1 when x equals L. So I set x equal to L. And everything would cancel out and I get 1. So the idea here is, because this function equals 1 at x equals 0, and this fraction equals 0 when x equals 0, then when I plug in x equals 0, it has the effect of selecting k1. Similarly, if I set x equals L throughout this whole thing, I get 0 over here, 1 over here, and it selects the value I want there, k2. So this is what Lagrange interpolation means in the linear case. So, so the idea is, since I want to have this value at 0, I have x minus the other point, and then I have 0 minus the other point. I want k2 when x equals L. So then I'll have x minus the other point, which is 0, and then L minus the other point. So that technique works in general. And then all I've done over here is simplify everything I have, and this is what I get. So you can see here, if I plug in x equals 0, all this goes away and I get k1. If I plug in x equal L, this fraction will cancel, the k1s will cancel, and I get k2. Questions about why this function works?
So why does it follow that that since the derivative of b with respect to t is 0, that the partial derivative of x twice taken is equal to 0?
Oh, this does not follow directly from this. That's going to happen, but the idea is, what I'd like to do is have my new solution for my transform problem satisfy the same PDE as the original one. But since the PDE is linear, if this satisfies the PDE and this satisfies the PDE, then this has to also. And because it's a function of x, I know it's going to satisfy this because there's no t dependence.
Okay.
But the only way it can satisfy the PDE and this is for it to satisfy this too. And this must be also be 0.
Okay, and by linear we mean that the solution is a linear function, right?
Yeah, that's linear at x. In other words, it has a form mx plus b.
Okay.
Where m and b are constants.
So does that mean that b is at most a linear solution, or that it can be a constant as well?
Okay. A constant function might not work. In fact, the only way it would work is if k1 and k2 were the same.
Okay.
Yeah. But for a situation like this, where you have these, where you're setting value of u at the boundary, a linear function, that's as far as you need to go. That you can find a linear function that will work. Now, that's not necessarily true for some other boundary conditions, but it does work for this one. So the result of this is your transform problem is right here. So capital U satisfies the same PDE as little u in the original problem. Similar form of boundary conditions, except now these values are 0. But then look closely at the initial condition. The previous initial condition only had 5x here. But because of this relationship, in other words, capital U is equal to little u minus b. And that's true for all time. So if I plug in t equals 0, I would get 5x over here, which is the original initial condition. And then to get capital U of x0, to solve for that, I need to take this term and move it to the other side. So when you find your function capital B of x, you must remember to subtract it from the initial condition to get the original initial condition for the new problem. So by making these values 0, the trade-off is that now we have this. But now this problem can be solved using separation of variables. And then once you have solved this problem by separation of variables, you go back to your original problem, and to get little u of x, you have this now. Just add on capital B of x, and you're done. You have this. The questions about this process. I'm going to do another example that's a bit more complicated than the first one. So here's our original problem. PDE initial conditions are the same. But now we have complications in the boundary conditions. First of all, our boundary values are functions of t now, instead of constants. Also, at the right endpoint, x equals L, we have a more complicated boundary condition because we're not just looking at value of u at the boundary, but also du dx at the boundary, and we're taking a combination of those values and saying that must equal this function. So we're still going to use the same general approach with some modifications. And so because of its more complicated boundary conditions, there's a bit more work involved. So here's how we're going to decompose the solution this time. So our boundary function now has to depend on t because of these boundary values depending on t, g1 and g2. Also, what we will find is that the PDE from a new problem, so solving for capital U, will not be exactly the same. And we'll see what that means when we get to that point. So we're still going to have a linear function of x to satisfy boundary conditions, but there's going to be a t dependence involved. But at least in terms of being a function of x, it's still simple in that regard. So we're still going to use you can still use the same interpolation approach because at x equals 0, we want this function to be equal to g1. Now, because of a more complicated boundary condition over here, we don't know exactly what we want this to be, what we want u to be equal to at this point. But so that's why this part is left unspecified. We don't know what k2 is. So, but the idea is I'm setting up a function that's linear in x that will be equal to g1 at x equals 0 and will be equal to this, whatever this is, at x equals L. So, but the way this function is set up is exactly the same as in the previous example. It's just that now we have functions of t here and here instead of constants. So you can see that if I plug in x equals 0, I'll get g1. And if I plug in x equals L, I'll have this simplified to 1, I have cancellation, and I'll get k2. So the idea is we're now going to use the second boundary condition at the right endpoint to figure out what k2 should be. Questions so far before I... So what I do is, here's my boundary condition at the right endpoint, taken from the original problem. So now I take this and substitute it into this boundary condition. And this is what I get. So here I took the derivative of this with respect to x. So that's here. And then I want the value of this at x equals L, and that gives me all of this. But this is going to simplify quite a bit because the terms involving g1 will cancel out. And because of the original boundary condition, I know that I need this to equal g2 of t, which is given. So now I have this equation where everything in here is known except for k2, because g1 and g2 are both given. So now I can solve this equation for K2. So it takes a bit of algebra, and this is what I get. So now I can take this K2, this whole expression, and substitute it for K2 in here. And there's some simplifying that can be done. And this is what I get for capital S of xt. So this is a function that is linear in x. Notice this is the only dependence on x that satisfies both of these boundary conditions. So you can see the whole procedure for finding capital S here. So I need a linear function that I know will satisfy the left boundary condition. That's simpler. And then will be equal to some unknown function K2 at the right endpoint. I then use this value at x equals L and also its derivative at x equals L to plug into the right boundary condition, and then require that the result equal my right boundary value, G2. This I can solve for K2. Getting K2, putting it back in here gives me capital S. And now I have my boundary function completely specified. Questions at this point? Now, I need a transform problem. This works out much like the previous example. Same boundary conditions, except now you have 0 on the right-hand sides. The initial condition, you have your original initial condition, minus your boundary function. Now keep in mind, that's a function of t also, but you have to set t equals 0. But you're still subtracting that off. Now your PDE is changed, though. So because S depends on t, ds dt is non-zero. It has to be subtracted off. Actually, what I'm going to do here, I'm going to return to the original PDE to show you how we get the new one. And this is a viewpoint that works well in general. Because we have our original solution, little u of xt, it's capital U of xt, plus capital S of xt. So now if I take this whole expression and substitute it into the original PDE that little u satisfies, then I have, whoops, okay, plus S derivative of respect to t is equal to alpha squared u plus S xx. And this comes from the fact that we have the original PDE that little u satisfies, but little u is equal to this. So I'm just filling this in here, and this is what I get. But capital S is a linear function of x. So Sxx is equal to 0. So that term I can toss out. Now I can just rearrange and I'm done. Keep in mind that differentiation is linear. And you see how the new PDE comes about. So this is something you can always do to see, okay, if you're writing your solution in terms of an expression like this, and this is what you're going to solve for, what PDE does this satisfy? And you can go for these operations like these to figure out what that would be. Now, non-homogeneous PDEs, we do not yet know how to solve. Separation of variables cannot be applied to them directly. That is something I will come to pretty soon, though. And approach kind of similar to separation of variables can be used. But it's easier to deal with that and homogeneous boundary conditions than to try to deal with the original homogeneous PDE and non-homogeneous boundary conditions. So what you would do is, like the previous example, you solve this problem, and then you have your solution capital U, add on capital S, and then you have your solution to the original problem. Any questions about this example? Now I'm going to try to get as general as I can. This won't cover all possible cases, but I'll elaborate on that at the end. Here we have more general boundary conditions. So at x equals 0, we have some linear combination of value of u and u dx equal to some given function g1, and then same kind of situation at the other boundary. So from a first example that we saw, these values were constants k1 and k2. Alpha 1 and alpha 2 were both equal to 1. Beta 1 and beta 2 were both equal to 0. Whereas in the second example, this was 1. This was some value h. This was 1. Beta 1 was 0. And alpha 1 was 1. And then we had g1 and g2 over here. So what I can show you how to do is for most boundary conditions that have this form, how to obtain a linear function in x that will satisfy these two boundary conditions. And then you can do what was done up here and transform your PDE and obtain a new problem like this one to solve for capital U. And you're going to see some linear algebra along the way that can be helpful in a lot of situations. So this is going to be pretty similar to what I've just shown you, but again, more general. So using the Lagrange interpolation I showed you earlier, or again, finding the equation of a line passing through 2 points, you can always do this, that this function, when x is equal to 0, you'll get k1. And when x is equal to L, this goes away, this fraction goes away, and you get k2. K1 and k2 are unknown at this point, but we use the boundary conditions to get them, like I did in the second example. So this function is designed to have this effect. So if you're working on like a homework problem or a problem test, you could just jump directly to this instead of working with those fractions that I showed you earlier. Now, for working with these boundary conditions, I need the derivative of this with respect to x, and that's what I have here. So now I'm going to take this and its derivative and substitute their values at x equals 0 and x equals L into these boundary conditions. Once I do that, this is what I have. Now, in these two equations, I have two unknowns, k1 and k2. And these are linear equations. So I'm having to solve a system of two linear equations in two unknowns. Definitely something you would know how to do from previous math courses. We're studying most closely and most in depth in, say, Math 326, linear algebra. I'm not assuming you remember all that, but I can show you how to proceed. Again, I like to work with solution formulas whenever possible. What I've done here is rearranged these equations. I want to have something times k1 plus something times k2 up here and down here. And that's what I've done. So just grouping by terms multiplying k1 or k2. So then what I can do is rewrite the system in matrix vector form. So for convenience, to make things a little less cluttered, I factored out a 1 over L throughout. So then I have this matrix times the vector k1 and k2 equals the vector g1, g2. And the reason why I've done this is I can use this equation written in this form to get myself a solution formula. Because I can use a formula for the inverse of a 2 by 2 matrix, which I've repeated here. This is a formula that I would say is well worth memorizing. It comes up so often in so many settings. So we have 1 over determinant and then this matrix that's obtained from the entries of this one. So then what I can do, this is a bit of a mess. So I can say k1 and k2 is equal to the inverse matrix times the vector g1 and g2. And here all I'm doing is I'm carrying out the matrix multiplication. So now I know what k1 and k2 are. K1 is equal to this first element times this fraction, and k2 is equal to the second element times this whole fraction. Again, quite a mess. But in a real problem, you would have values given for alpha 1, alpha 2, beta 1, beta 2 that would be plugged in here. And some of those may be 0. So that would simplify the expression dramatically. So, and the key here is to get these formulas for k1 and k2, because once you have them, and you see that they're in terms of your given boundary values, g1 and g2, then you can substitute k1 and k2 in here. And then you have your boundary function, capital S of xt. And then you can go back to your original problem, and you get a transformed problem that's much like this one, with the appropriate boundary conditions here and here. But based on the procedure I've shown you, the PDE and boundary conditions would be exactly, the PDE and initial conditions would be exactly these. And then your whatever homogeneous boundary conditions you have. Do you have any questions about this general procedure. For a real problem, you could jump directly to this formula for K1 and K2. You wouldn't have to go through all this. But you can take what this gives you for your particular problem, substitute those into here. So that's how you would actually apply this to a problem. Now, there's one important case I should talk about where this idea doesn't work. If you have boundary conditions that specify only the value of du dx at the boundary points, so in other words, you don't have this term or this term, meaning alpha 1 and alpha 2 are both 0, then we have a problem, because if I go to my formulas here for K1 and K2, if I set alpha 1 and alpha 2 both equal to 0, I'm going to get 0 down here. In other words, the matrix that we have here, if I get rid of the both alpha terms, the matrix is not invertible, also known as singular. So this system of equations does not have a solution if alpha 1 and alpha 2 are 0. So in the case of Neumann boundary conditions, where alpha 1 and alpha 2 are 0, and beta 1 and beta 2 are both equal to 1, we have to, unfortunately, in that case, we do have to try a different approach. And that's what I described here. So let's suppose that these are your boundary conditions. So in this case, you cannot find a function that is linear in x such that its derivative is equal to g1 at x equals 0 and g2 at x equals L. The reason, and a nonlinear algebra way to see that is, suppose u satisfies these boundary conditions and it's a linear function in x. Well, then you take a derivative with respect to x, and that's because u is linear, its derivative is going to be a constant. You're not going to have a constant function be equal to g1 at one endpoint and g2 at another. It's just not possible. So instead, what you need to do is work on it with a derivative. So I let v be equal to du dx. So v satisfies Dirichlet or type 1 boundary conditions. So for this situation, I know how to solve for v in this case. And that just goes back to our first example. So you find your boundary condition, your boundary function that satisfies these boundary conditions. So you can find a linear function that does this. But now you need to work your way back to u. So what you found here, this is not your boundary function, it's the derivative of it with respect to x. So you integrate it. So when you have Neumann or type 3 boundary conditions, you can find a quadratic function of x that satisfies these. So that's what's done here. You find a linear function that handles this, integrate it to get a quadratic function, and then you're done. So the general procedure I described earlier is only helpful in the case where it's possible to find a linear function that satisfies your boundary conditions. So at least in a case like this, there's a way around that. Questions about what I've shown here? Or of our homework questions?
I'm not sure how to start.
I'm going to unshare and reshare. Get the text. Hold on a second. Okay.
Yeah, that's the problem. Lesson 4, number 3.
Okay. All right. Hold on. All right. This is lesson 4, number 3.
Yes.
Okay. All right. So all right. Sorry, the hell stuff happening on my screen. So okay, I'm gonna dig up the notes for this part. Okay, so that would have been lesson 4. So that would be. All right. Okay, so here's the derivation from before, for a case where we have k being a constant. So for most part, the derivation is going to be the same, except I'm just going to point out where it differs. So if we look at where okay. Where this coefficient k is now being a function of x, that means that k cannot be factored to be put out here. K needs to be evaluated at x for this term and evaluated at x plus delta x for this term. So that's one thing I would change. The other thing is, here, for both derivations, you have a difference of function values that are evaluated at different x's. And what I did with that last time, you will do again here, where you express it as an integral of its derivative. And in the previous time, the expression that we had here was k times ux, and that led to kuxx over here. But now, again, whatever you have here that's being evaluated at two different x values, you must include its derivative here. And when you do that, and then proceed with the derivation exactly as last time, this will fall out.
Okay, thank you.
Okay. Other homework questions? Quite bunch, I see.
Are there practice problems in this book?
Um, Not really. There will be practice problems in advance of the tests. That's something I'll put out when it gets closer to that time, and also solutions. But yeah, all the book offers are like whatever examples they have.
Okay, I'll wait patiently then.
Okay. Last chance for any questions. Of course, you can also contact me later. Okay, I think that's sufficient awkward silence. I'll stop recording here, and I guess I have extra time to get ready for next class. Um, so, um, again, you contact me directly if you have any remaining homework difficulties.